Hello everyone, my name is Mohammed BARAKAT. I'm an undergraduate mechanical engineering student at UT Tyler, and today I'll be sharing my work on silicon nanoparticle deformation using molecular dynamics with a machine learned potential. This research was funded by the NSF through the Texas A&M Online OREU program, and I'd also like to thank the HPRC, High Performance Research Computing Center for Computational Resources, as well as my faculty advisor, Dr. Wei Gao, and the PhD student I've been working closely with, Zia Ding, for their continued guidance and support. So for a little bit of background, there are three key ideas driving this project. The first one is size. Bulk silicon is well studied and there's decades of research on it, and its mechanics are very well modeled. However, when we move on to the nanoscale, there's this knowledge gap and the mechanics of nanoscale silicon aren't understood as well. And this is important because nanoscale silicon has applications like semiconductors and NEMS. The second point is the shape. Many studies use these common simplified shapes like cubes and spheres for convenience, but the shape that you see on the right, which we call a wolf-shaped particle, is more stable in comparison to these common shapes and more physically realistic, and that's what we went for. The third thing is the potential, and you can think of the potential as basically like the physics rule that governs how atoms interact in a simulation. There is many studies and research done on classical potentials, and that's what's been used for a very long time, with the two most popular being Stillinger-Weber, SW, and Tursoff. However, there are relatively newer potentials that are machine learned based on data, like the Gaussian approximation potential, gap potential, that offer more accuracy, and we want to put that to the test. So that leads to our goal. Our goal is to model the deformation for a wolf-like shape of nanoscale silicon using a machine learning potential. Now, to do this, we follow a simple four-step workflow, where first we make the shape using AtomSK and or this Python package called wolfpack, and then anneal it to generate this realistic free surface using lamps, and then compress it uniaxially along the z direction, also using lamps, and then analyze these results and provide meaningful conclusions using Oviedo and Python. And we repeat this process 3 times, once for SW, once for Tursoff, and once for gap, so we can directly compare their results and their predictions. Now, zooming in onto the formulation of the shape, we can see here that on the left we have a simulation paper that uses this wolf shape, and in the middle we have the actual wolf shape derived from an experimental paper, and this right hand column shows the shape that we generated using wolfpack. And this shape has a size of 10 nanometers and is approximately 45,000 atoms. So there are key differences between the experimental paper and simulation paper. For example, this 110 plane right here on the edges is not captured in the simulation paper, and we successfully managed to capture it, and this shows that our shape more closely matches the experimental shape, giving us confidence in using it as the base for our simulations. Now, looking at the actual 3 potentials side by side under compression, as you can see from SW, it shows these localized abrupt transitions, which we can say are probably dislocations or stacking faults. However, we cannot definitively make that conclusion yet. And then Tursoff shows a smoother, more distributed gradual change, suggesting widespread plasticity. And gap is kind of like an in-between mix, where it shows that localized disorder, but that grows gradually, and it shows a more physical looking progression. Now, these trends also align with the stress-strain curves. As you can see here, the SW has these dramatic drops and rises, which match the abrupt transitions we just saw in the crystal structure, and Tursoff has this smoother, more ductile-like behavior, and it seems to underestimate the resistance to plasticity. Meanwhile, gap provides a balance of both, showing the gradual evolution, but also showing a more ideal looking stress strain curve, and it looks closer to something we expect experimentally. Now, zooming in on the SW potential, we can see on the left here a coordination analysis along with a dislocation analysis on the right. And the coordination analysis is here to show that no phase transformation was captured, while dislocations were indeed captured. And this confirms that dislocation-driven plasticity is the dominant mechanism shown. However, Tursoff shows the opposite. We see the entropy of the particle gradually rising, and on the right here we see two radial distribution function plots where the probability of a given pair separation distance is shown. The top one shows more defined peaks, which means that the atoms are more organized and it is a more crystalline structure, specifically silicon 1. And on the bottom you can see that the second and third peak almost merged into this plateau looking shape, which shows that the atoms ordering changed, yielding to a phase transition. And since the first peak didn't really change that much in comparison to the second and third, that leads to classic amorphization or metastable transition. Looking at the gap, we can see the coordination analysis shows us that a phase transformation was indeed captured along with the dislocations. So taking a deeper look into the phase transformations like we did for Tursoff, we can see the same general RDF transition. And there's a really interesting thing here where you can see the increase in very high entropy atoms, which mean that the atoms are more disordered. And in the experimental paper that I mentioned before and looked deeper into on the next slide, it suggests that the phase transformation for this is a silicon 1 to silicon 2 transformation, which are two ordered transformations. However, looking at the entropy here, we can see that it is indeed not a silicon 1 to silicon 2, rather a silicon 1 to an amorphous phase or a metastable phase. And that's one of the most interesting findings of this project because it goes against what the experimental paper assumed. Now, looking at that experimental paper that I was talking about, we can see here a sequence of TEM images of the particle under compression in comparison to the machine learning potential, and we can see that the machine learning potential has a very similar deformation features, and this outlined part right here that the arrow is pointing to, the paper said that it is an embryo for a dislocation, and that matches what we found. So the gap potential not only captures the physics, but it also aligns well with the experiment. So, in conclusion, the SW potential found the dislocations but missed the transformations, while the Tursoff potential found the transformations and missed the dislocation, and the machine learning potential, gap potential, captured both and matched the experiment the best. So for the next steps, it would be to look at how the material behaves under differing orientations. So taking this shape that we looked at before and rotating it so that the blue 111 plane is at the top or the 110 plane is at the top, and then compressing it and seeing how it behaves, along with strain rate sensitivity, looking into 10 to the 8 and 10 to the 10, because what we're currently using and what's commonly found in literature is 10 to the 9 strain rate. So the next steps would be to look at one up and one down strain rate and seeing how it behaves. And yeah, that's my project. Thank you.